Okay, so this is the last speaker of this morning session. Is Paulo Faria Junior, and he's going to talk about proximity effects in excitons of two-dimensional van der Waals semiconductors. So.
Thank you, Chairman. I would like to thank the organizers once again for giving me the opportunity to be here at the stage one more time. I was here last week. And I would also like to thank Igor for the nice talk about excitons. You just made my life much easier. And yeah, as the title mentions, I'm going to talk about proximity effects in excitons in two-dimensional van der Waals semiconductors. But as the first speaker from Yaro's group, let me just introduce you where we're coming from. We're from the Spintronics research group and from Professor Jaroslav Fabian. We are located here in Regensburg, which is just 1.5 hours from Munich. The city is quite old, and these are the two most famous landmarks. There is the Stone Bridge and the St. Peter's Cathedral. The University of Regensburg has this sort of style, very sharp edges, and we also have a lake, and sometimes we have sunny days. This is a picture taken one of these days. And this is the most recent picture of the group. The guys that I named here are the people you would see around here at the conference. You can also see Igor here lurking in the back. So the summary of my talk is essentially we would like to give an overview of exciton physics, complementing what Igor mentioned, specifically focusing on this effective Bethe-Salpeter equation approach. I will also just briefly show you an example in 3D related to indium phosphide wurtzite nanowires, which was the first project that we applied this framework of the Bethe-Salpeter equation. Then I move on to phosphorene, not only talking about excitons, but also about G factors. And then I move on to the proximity exchange effect in TMDCS and chromium triiodide. So pictorially, we can imagine that an exciton is an electron and a hole interacting via Coulomb. And this is a concept that was already introduced in the 1930s. And typically what rules the exciton is the band structure, if you're thinking in a simple way, the effective mass of these two carriers, and also the dielectric environment, or the material that it's surrounded. And this is an intrinsic many-body phenomena. An electron and a hole interacting is intrinsic many-body phenomena, which means that this typical picture that we have of band structure is not very good to understanding what's happening with the exciton. A better picture would be something like this. So the electron-hole interaction would create some bound states and some continuum states. This continuum state would be essentially defined by the band gap, and the first exciton states is separated by the continuum by this energy that we call the binding energy. As a signature of this exciton, we can, for instance, observe this in the absorption, and what we would see is if we had just single particle, this is depicted by the dashed line here. If we include the excitonic interaction, then we see some peaks, and the spectra is shifted below the band gap. And there's also some renormalization because electron-hole interaction also affects the continuum. If we compare 3D and 2D from a textbook perspective, and what I mean textbook is we assume parabolic bands. Carriers are defined by the effective masses. The Coulomb potential is just 1/r in 3D and 2D, which means that what we have to solve is a hydrogen atom problem. And if we do this in 3D and 2D, we will find something like this. So 2D essentially adds a 4 here to the binding energy of the exciton, if we keep all these other constants the same. And the absorption signature, this is the picture I showed in the last slide, and this would be the picture that we see in 2D. So we also see the peaks and this increase of the absorption spectra. One thing that is interesting about the materials is that once we look at the dielectric screening, essentially the surroundings of where these electrons are interacting, in 3D materials, typical 3-5 semiconductors, there's a strong screening, which leads to binding energies of 5 millielectron volts. In 2D materials, we can imagine that these few lines are now going outside the material, and there's a weak screening, which leads to binding energies of 500 millielectron volts. If we contrast this to the energy at room temperature of 25 millielectron volts, these 2D materials are a very interesting and attractive platform to study exciton physics at room temperature. So you don't need to cool down your sample. At room temperature, you can see these effects. And let me show you some experimental measurements where we can see the exciton signature. Here on the left side, I show you bulk gallium arsenide in zinc blende. And as we decrease the temperature, we start to see the peak. At close to room temperature, this peak of the exciton nearly vanishes. Another example here is indium phosphide wurtzite nanowires. Nanowires, in this case, they have very large diameter, so essentially they are a bulk. And the same feature we see here, if we decrease the temperature, we start to see the exciton peaks, and they vanish as we move to room temperature. On the other hand, for 2D materials, for instance, MOSC2, this was the first demonstration that MOSC2 is a direct band gap semiconductor at monolayer level. The exciton peaks, A and B, are already present at room temperature. And actually, if we decrease the temperature, we can track this hydrogen series of the excitons. And this was measured in this paper here. To calculate these excitons theoretically, we employ the Bethe-Salpeter equation, and I just provide this reference here where they gave the equation on this form, but any of the references that from Igor's work would suffice to describe the Bethe-Salpeter equation. And essentially what this equation tells us is that this is an eigenvalue problem, where we would find the exciton binding energy and the exciton envelope function, which would be connected to the total exciton wave function this way. These two terms here are the direct term, direct Coulomb interaction, given this way, Coulomb term here. And this other one is the exchange term, which is essentially exchanging this x and x prime and taking the sign out. And I put it in red because it will be 0 in all the things that I'm going to mention here. And if we look at this equation, essentially there are two main ingredients. One is the single particle spectra, conduction and valence band, energies and wave functions, and the bare Coulomb potential. And the approach that we use is sometimes we have to do it numerically, so we need to take care to worry about numerical convergency by how it scales with the number of K points, the space of the K space that we consider, and also if we have multi-band Hamiltonians and complicated systems, which bands we include in the calculations. Regarding the single particle spectra, sorry, we typically start from first principle calculations, which would give a complete picture of the band structure. But most of the time, we're only interested in the physics around the band edge, so very close to the band gap. Some bands would just be responsible from the physics there, and therefore it's convenient to apply some effective modeling. The most two conventional approaches would be the K.P method or the time binding. And here I depict what would be the main differences and similarities between them. In the K.P, we usually talk about the period part of the block function in different bands, N or M, and at specific K points, and how they interact among themselves. For the tight binding, we usually talk about orbitals, or things that resemble orbitals, things that are localized, and the connection between them. And in K.P, we typically call these couplings K.P parameters, and in tight binding, hopping parameters. And one of the similar things that these two methods have is that they both rely on symmetry analysis. So you need some group theory input to find this non-zero matrix elements. And if you want to replicate your ab initio band structure, then some numerical procedure, some fitting procedure, often done numerically, is also necessary. The second ingredient is the bare Coulomb potential, which essentially can be found by solving the Poisson equation. And given the dielectric environment, this epsilon here can be a tensor and spatial dependent, and this equation can be hard to solve. Just to give you some examples, if we solve this in 2D with an isotropic dielectric environment, we would find a potential like this. If we take the Coulomb potential in 2D, which is not a solution of the Poisson equation, but you just take 1 over r and you take out the z part, you would find a potential like this. But for these 2D materials, it was shown that the potential that best describes the physics is the so-called Ritowa-Keldysh potential. And essentially, to arrive at this potential, you consider that your dielectric function varies in z direction, from top material to the 2D material to the bottom material. You plug this, solve the Poisson equation, and you take the limit of kd much smaller than 1. And then you would arrive at this equation like this. And notice that the powers of k in the Ritowa-Keldysh resemble these two other functions here. If we go to the real space, then the potential is given like this. H0 is the Struve function, Y0 is the Bessel function of second kind. And the two parameters that control this potential are the dielectric surrounding, the average of top and bottom dielectric constant, and the screening length, which would be a property of this 2D material that we're talking about, which is connected to the dielectric constant of this 2D material. Just to give you an example of how the binding energy converges when we look at numerical solutions of the Bethe-Salpeter equation, I show you here this example, which is this dashed line is the analytical solution for the hydrogen atom. And if we increase the size of our k-space and start increasing the points, so going towards this direction, the energy starts to converge to this value. If we take a linear extrapolation and we plot how this energy evolves as we are increasing the k limit, then we see that it really converges to the analytical result. Now if we turn on the effect of the screening length, what happens to the binding energy is that it goes up. So the Ritowa-Keldysh potential gives binding energies above the typical hydrogen atom. And actually this was already observed experimentally in WSC2. If we look here, theory, what they mean by theory here is using the Ritowa-Keldysh potential, and the red solid line here is the 2D hydrogen atom. So essentially, what they measure experimentally is above what the hydrogen atom potential would give. And this is what's depicted here. And the understanding is the fact that you have this screening from the outside, as I mentioned before. As a realistic example in 3D, let me just briefly mention this work that we have done on wurtzite materials. We actually started looking at indium phosphide, just trying to describe the band structure from ab initio using an effective K.P model that includes the spin splitting effects that describes here, for instance, valence band and conduction band. And this was done during my PhD with Professor Guilherme Cipai. And after that, we got interested in excitons, and using this effective model, we could compute the bulk exciton binding energy, and we found something of 6.9 millielectron volts. From an experimental point of view, they can directly measure the exciton effective mass, and with this value, they can estimate or calculate a binding energy of 6.4 millielectron volts. So our calculations are in very good agreement with what they found. But we went one step further, and we looked at how these excitons behave when they are on an external magnetic field. And this is summarized in this plot here. So this is the Zeeman splitting of the PL peak. So you apply magnetic field, the PL peak starts to go away from each other. You take the peaks, the difference, and you plot, and you have the Zeeman splitting. And because wurtzite is anisotropic, if you apply magnetic field along the nanowire axis or perpendicular, you find a different trend. So, and along the nanowire axis, you see this nonlinear feature. And we applied the Bethe-Salpeter equation using the Landau levels as a single particle input. And what we found is that our calculations are in very good agreement with the experimental measurements. And actually, this nonlinear feature here was observed in other wurtzite materials, and we were able to show in this follow-up study that indeed this is a very general feature. We can show this numerically, and also from a effective modeling of the symmetries of wurtzite structure. So let's move on to the 2D world.
So, I have a question.
Yes.
So when you apply the magnetic field in plane, so Bx, so for high magnetic fields you can explain, so you have excitons, but for low magnetic fields you can also adopt a single particle.
The point is that when the magnetic field is small, we need to include a lot of Landau levels, and this would make the calculations take much more time. So we decided to stop here for the purpose of the physics would be the same as the single particle. So about phosphorene, it's a direct band gap semiconductor material, not only in the monolayer, but also if you have a few layers of this material, which is very interesting because if we compare how the band gaps of conventional semiconductors span in the energy range, black phosphor or phosphorene and many layers can bridge this energy range and connect to the TMDCs here. And for instance, in this review here of optics in 2D materials, it is listed as one of the most famous materials alongside boron nitride, TMDCs, and graphene. But we're actually interested in phosphorene from the perspective of spintronics. We heard yesterday the talk of Martin, and he was discussing the spin relaxation mechanisms. And phosphorene is anisotropic in all the three directions. And essentially, they, in this work, computed the spin relaxation time on via the Elliott-Jaffet mechanism and the Diakonov-Peral mechanism. And we can see that it's really anisotropic. In a follow-up study, in collaboration with Ahmed, that is also here, they could really show that if you take phosphorene, make the spin valve operation, what is really happening there is that this Elliott-Jaffet spin relaxation is taking place. There are also many reports on transport experiments for holes and electrons in this material. And what is interesting is that they apply an external magnetic field to measure the resistance. And with that, they can compute the G factors. If we think about the K.P approach, one way to compute G factors is to write some perturbative equation like this. This pi operator here is essentially the velocity operator, which takes into account the linear momentum, but also the spin-warp coupling term. And in phosphorene, what happens is, if you don't include this term, essentially, you would not be able to see any modification to the G factor. And this is due to the anisotropic character of the crystal structure. And one question that we really wanted to investigate is, what is the value of the intrinsic G factor in monolayer phosphorene, which is a result of these couplings here between these two different directions. So what we did, we started from a band structure calculation from ab initio, and we applied a K.P modeling to describe the bands around the band gap. And here we did different models, including different interactions. But to summarize everything, this P parameter, we found this value here. And for the alpha parameter, we found that it's actually 2 orders of magnitude smaller than this P parameter. And if we compute the G factors with these values here, then we found that, first of all, we cannot assign the sign of alpha, could be plus or minus here for the band structure. But in the G factor, it would essentially mean that G factor is slightly above 2 or slightly below 2. But it stays nearly almost 2. And if we look at the experiments, for transport experiments in the valence band, those reports from the previous slide provide these values here. For conduction band, there are some reports that provide this, that it could be below 2.5. And if we look at the other theoretical attempts, which are actually before our paper, this was the only one, they found a G factor of 2.14, assuming an alpha of 0.45. But this alpha was not calculated, but actually estimated from some experimental data that they had. And after our paper, when our paper was in preparation, there was this new archive paper that calculated also this alpha from ab initio. He did not include the gap correction, but anyhow, this doesn't change the physics. And the alpha is on the order of magnitude of what we found. And the G factor is really much closer than 2 than this value here. So this brings to the point that in this particular case, if we have deviations from the G factor value that around 2, this is beyond the intrinsic features of phosphorene and related to many body effects, particularly the exchange interaction between the electrons or the holes. But since phosphorene is also a direct band gap material, it's also convenient to compute the excitons using those effective models combined with the Bethe-Salpeter equation. So here I show you the binding energy for the first 3 exciton states scaling with the dielectric environment. This is the diameter of the exciton wave function in x and y direction. And let's first look at the binding energy. If we compare freestanding phosphorene, phosphorene on silicon dioxide substrate, and boron nitride encapsulated phosphorene of our calculations to what is found in the literature, then we see that we have a very good agreement with the values provided in the literature. And I like to point out that within this range here, all the citations can be found in our paper, There are many, many different approaches. Fully ab initio, fully effective models, experimental estimations. So we are within the range that people have been investigating. And to look at the diameter, it's convenient to look at the exciton envelope functions themselves. So here on this top part, I show you how the envelope functions would look if we have vacuum, freestanding phosphorene, or if phosphorene is encapsulated by boron nitride. This row here is in the reciprocal space, and this row here is in the real space. And essentially what we see is, if we have an exciton that is elongated in reciprocal space, it will be shrinked in real space. So localized excitons in K space are extended excitons in real space and vice versa. And this somehow gives you a hint of how large your space should be when you're numerically solving the Bethe-Salpeter equation. Let me now move to the promised part of the talk related to proximity exchange effect, which Igor already mentioned a little bit. And essentially, we are interested in this van der Waals heterostructures from the perspective of proximity effects. So when we combine 2D materials, they already have very interesting properties, but once we put them together, we can have a very rich playground to study new physics and maybe find new functionalities. And proximity effects, we heard on the talks yesterday, on the tutorials and other talks, that this is a very important way to understand the effect of one material on the other. And I also mentioned here the review that Igor mentioned in his talk. And just to mention a few examples of that we are doing in the group, I show here proximitized graphene systems. So essentially, if you take graphene and put on TMDC, we already heard that this induces a spin-warp coupling. And depending on the TMDC, you can even invert the band gap of the material. And I'm pretty sure Martin will talk more about this in the afternoon. Another example is if you take bilayer graphene and put on a ferromagnet, chromium, germanium, tellurium, you induce an exchange coupling, and which is the same for both values. So because of the ferromagnet character of the material, you break time reversal symmetry, and you can have spin polarized carriers in the two valleys. We're actually interested in TMDCs and how this proximity exchange would affect them. If we look at bare monolayer TMDCs, then essentially the exciton G factors that you would measure in a PL experiment under magnetic field, they would amount to roughly around 4, which means that at 10 Tesla, this would be a 2.3 milli electron volt splitting. If you take TMDC and put on a magnetic substrate, as actually Igor mentioned about this in the previous talk, valley splitting is also another word for exciton G factor in TMDCs. So in this experiment, they saw an enhancement of this valley splitting when you apply magnetic field. But when you put TMDC on a magnetic substrate, what you would expect is that you don't have to apply magnetic field to see this valley splitting. Actually, theory predicts that at 0 magnetic field, you should find a 10 milli electron volt splitting. The problem is, in this particular construction, there are surface issues, for instance, polycrystallinity or terminations that reduce this intrinsic splitting that you would expect. However, you can lift this if you go to the ultra-thin van der Waals ferromagnet. For instance, chromium triiodide. In this recent experiment, they showed that placing tungsten diselenide on top of this chromium triiodide, it is possible to find a 3.5 milli electron volt splitting at 0 magnetic field. And this amount essentially means, comparing with the bare monolayer TMDC, is as if you had a 13 Tesla magnetic field into your sample. And this is actually the kind of material we're interested. And this is what I'm going to mention to you right now. So we place a TMDC on top of chromium triiodide. And we also are interested in the effects of external electric field and twisting between these two layers. And one thing that we found is that this proximity exchange is a very short range effect. And why is that? We placed a second TMDC on top of this TMDC here, and it feels nearly no effect of this chromium triiodide. We placed a second chromium triiodide below this one, either with ferromagnet or antiferromagnet alignment, and it does not affect this TMDC here. We also added a boron nitride between the TMDC and the chromium triiodide, and we saw that the proximity exchange decreased by 2 orders of magnitude. So essentially, what is happening is very close, is the chromium triiodide and the TMDC close to it. Just to give you an example of the supercells with the twisting, if we have 0 twist, then we essentially have a supercell of 20 atoms. If we twist, in this case, we investigated the 30-degree twist, we have a supercell of 243 atoms. This is an example of the band structure of MoSe2 on chromium triiodide. Here there is no twist, no electric field, and spin-orbit coupling. And here we can see that the TMDC bands are shown here and here. In between the band gap, we have some chromium bands, but the TMDC bands can be nicely described by the time binding model, including the exchange effect, which we see here that this energy is slightly different than this one. And despite of what we do, either twisting or changing the electric field, what would happen, what we want to see in the excitonic perspective is coming from these bands here. So we are plotting the 2 valence bands with the same energy, just so we could just look at the conduction band, and these effects will essentially change this energy. And then we would see the signature in the excitonic spectra, which the absorption would look something like this. So we have here the A excitons, here the B excitons, and as Igor mentioned, the B exciton has the reversed value splitting as the A exciton. And if we change electric field, we see that this separation shown here by this solid and dashed line are changing, and also if we twist, it also changes. And here in gray line, we show the single particle, what we would expect from a single particle perspective. If we twist the angle from 0 to 30 degrees, no external electric field here, we see that for MoSe2, there's a 3.4-fold increase in the value splitting. For WSe2, there's a 4.4-fold increase in the value splitting. By tuning the electric field, and these are results for 0 angle, we see that we can change by few millielectron volts this value splitting that we observe. And here, we show that the exciton value splitting compares quite well if we have analyzed from a single particle perspective. Of course, you cannot do dynamics or talk about binding energies, but if you just want a rough estimate of how much this value splitting would be, single particle, at least for this case, would be enough. And actually, I'm arriving at the end of my talk. I would like to acknowledge the people involved. So to the materials, these people here, indium wurtzite nanowires, the group of Antonio, the K.P modeling of wurtzite, Guilherme, and valuable discussions with other co-workers. And these people colored here are from the people from Yaro's group that you would, or that were in Yaro's group that you would see here around in the conference. I also would like to acknowledge the financial support, and just a few words about the Alexander von Humboldt Foundation. If you're finishing your PhD and looking for a postdoc, and you are interested to go to Germany, Alexander von Humboldt Foundation is a nice opportunity to do so. Actually, if you're also experienced researcher, you can also apply for grants in the Humboldt Foundation. And when you get the grant, it's not only the grant to be there, but you actually have a lot of benefits once your grant's finished. You can come back many times. And as a curiosity, since we are in an audience of physicists, the first director of the Humboldt Foundation after the war, it was reestablished after the Second World War, was Werner Heisenberg. He was a director of the foundation for nearly 20 years. And here I summarize the topics I discussed. There are upcoming related studies that I have not mentioned due to time constraints, but if you're interested, I will be around and happy to discuss about it. Thank you for your time.
Questions? We have time for one question.
Paulo, do you think that the screening length which you are using in the Keldysh-Ritva potential would be dependent